So there are some periodic trends that we need to be aware of. These are trends, they're not absolutes. The size of atoms varies in a predictable way. So atomic size, one definition of that is the distance between the outermost electrons and the nucleus. So you can think of the radius from the nucleus to the outermost electrons. As you go across a period, those are the rows, from left to right, atomic size decreases. This is something that you would not expect because sodium has 11 electrons and 11 protons. Argon has 18 electrons, 18 protons. You would expect that argon would be larger, right? You would expect it to be bigger, but it's actually smaller. Do I have a good, I don't have a picture. I should add a picture here. Let's look at something smaller. Let's look at lithium and neon. So here's lithium. How many protons in lithium's nucleus? 3. So it's got 3 protons. And neon has how many protons? 10 protons. Okay, so lithium has 1 valence electron. What principal shell is that electron in? 2. So it has 1 electron in this n equals 2 shell. Here's where thinking of it more in terms of a Bohr atom. So then there's this inner one too. This is the n equals 1. Well, for neon, it also has 2 core electrons in n equals 1. But then in the n equals 2 level, it has how many? 8. I didn't draw that super well. This is the second level. This is the second level. N equals 2 is roughly the same distance from the nucleus for lithium and for neon. And so thinking of it that way, we would think, well, neon should be the same size as lithium. So why is it smaller? Well, there are 10 protons here pulling on these electrons. And over here, there's only 3 protons pulling on the electrons. This positive 10 charge is more attractive to the electrons. It pulls them in tighter. As you go from lithium to neon, the charge on the nucleus increases, and those electrons that are in the same principal shell, the valence electrons, are getting pulled in tighter because of that increasing charge on the nucleus. I think it's best to understand why the size decreases as you go across. But if you don't understand, you can just memorize it. That works too.
Are the drawings just for like reference? So it's not like a while back there was the little like clouds that they showed.
Yes.
And they're like weird.
These are just for a mental picture.
Okay.
The Bohr model is wrong, and yet it can still help us to understand some things.
You don't have to draw like the weird.
I'm not going to make you draw anything.
Okay.
I might show you a picture and ask you to choose which is the P and which is the S. That could happen, but I'm not going to make you draw anything because I don't want to look at your drawings and decide, is this one good enough? That's painful. So as you go across the periodic table, atoms get smaller. So that's backwards of what we expect. Going down a column, they get bigger, and that makes sense, right? You go lithium, sodium, potassium, you're adding electrons, you're adding protons. But more importantly, the electrons that are being added are going into higher and higher shells. And so it's getting bigger and bigger. So as you go down any group, the atoms get larger. So here is relative atomic sizes of the main group elements. And we see that as we go from lithium to neon, neon is significantly smaller than lithium. That's not what we expect. It decreases as we go across because of the increasing charge of the nucleus. As we start at the top of a column and move down, we see that the atoms get larger. That makes sense. Doesn't matter which column you look at, that happens.
Good question.
Mm-hmm.
Is it just the outer electrons that determine that pull, the strength of the pull?
It's actually the charge on the nucleus, the number of protons. So we should be able to answer questions like this. Choose the larger atom in each pair. So lead or polonium. We got to find them. So here's lead, here's polonium. And somebody said lead. Yes, lead is larger. As we go across, they get smaller. So lead is the larger atom in the pair. What about rubidium and sodium? Here's sodium and rubidium. Yeah, so rubidium is larger because it's below. As you go down, they get bigger. Tin or bismuth? Let's pick a different color here. So here's bismuth and here's tin. Well, let's look at the trends. If we're going down, bismuth is below tin, so that would predict bismuth being larger. But if we go across, they're getting smaller, that would predict that bismuth is smaller.
Do they cancel out?
I would say
Similar?
they're going to cancel out. You really can't tell for sure. And I would not make you guess on an exam. So just can't tell on that one. What about fluorine or selenium? Selenium. Yeah. So here we've got fluorine, and here we've got selenium. And again, they're not in the same row or the same column. But as we go across, we predict that fluorine is smaller. As we go down, we predict that fluorine is smaller. The two trends reinforce each other instead of contradicting. So selenium is going to be larger. So if the two trends oppose each other, just throw your hands up and say, I can't tell. If they both point in the same direction, then we can tell. Another trend is ionization energy. Ionization energy is the energy needed to remove an electron from an atom. So we've been talking about sodium and sodium wanting to lose an electron to become like neon. Well, sodium doesn't just give it up. You have to give it something in exchange. You have to give it some energy for it to give you its electron. How much energy you have to give it depends on what element you're looking at. And there's a trend in that ionization energy. Ionization energy increases as you move to the right across a period. So one way to remember this is if you remove an electron from a group 1A element, you're going to get a noble gas configuration. That's a good thing, right? If you remove an electron from a group 7A element, that's making that element worse, right? The group 7A elements want to gain an electron so that they can become like the noble gases. If you take an electron away, it's going to be really unhappy about that. So the ionization energy for group 7 is going to be much higher than for group 1. The other explanation is as you go across the period, the atoms get smaller. And those outer electrons are closer to the nucleus, and so they're harder to pull off. Ionization energy decreases as you go down a column. The atoms are getting larger and larger and larger, and it's easier to pull one off. I have this very politically incorrect analogy for that. So I've got 6 kids. I go to the fair. Actually, I don't go to the fair because I have 6 kids, but hypothetically, take all 6 kids to the fair. And a friend of mine who only has 1 child takes her kid to the fair. So which family is it easier to kidnap a child from?
Oh.
Yeah, politically incorrect, right? It'd be much easier to take one of my kids. Because there's 6 of them, right? They're all over the place. I can't hold on to all of them. I only have 2 hands. My friend with 1 child probably has an iron grip on that kid's hand. There's no way you're going to get that one kid. She's just focused on the one child, right? That's why I don't go to the fair, because I like my children most of the time and I don't want to lose them. So, never lost a child. But as you get a larger and larger atom, those electrons are on the outside. They're farther from the nucleus. It's easier to pull one off. So ionization energy decreases as the atom gets bigger. So ionization energy and atomic size, their trends are exactly opposite. Ionization energy increases as you go across, decreases as you go down. So choose the element with the higher ionization energy. So magnesium or strontium. So here's magnesium and here's strontium. Which one is going to be easier to take an electron from? Strontium is going to be easier. Yeah, so I asked the wrong question. So magnesium has the higher ionization energy. It's going to be harder to pull one off of magnesium. Magnesium is smaller. Indium or tellurium. So here's... So this is the higher ionization energy. Higher energy, more money, harder to remove. So we're supposed to choose the one with the higher. And I asked you the wrong question. I said, which would be easier? So strontium would be easier. That means magnesium's harder. I did that badly. Indium and tellurium, which one's harder to remove? Tellurium, because as we go across, they get smaller. So this one is closer. But we can also think, well, tellurium's in group 6A. We learned that that should make a -2 ion, right? It's not going to be happy about making a positive ion. It's a nonmetal, for one thing. Nonmetals don't make positive ions.
Wait, can you make ions, positive ions with those things? It's just hard?
You could, but it requires a lot of doing.
Oh.
Yeah.
Like for this class, we don't.
For this class, no. Nonmetals, except for hydrogen, do not make positive ions. Hydrogen has to be an exception to everything. Higher ionization energy would be tellurium. Copper or phosphorus. So here's copper, carbon or phosphorus. Well, as you go across, ionization energy gets higher, but as you go down, it gets lower. So these trends are opposing each other. One predicts carbon, one predicts phosphorus. So say, can't tell. Fluorine and sulfur. I better get a different color out here. Here's fluorine, and here's sulfur. Well, as we go across, ionization energy increases, predicting that fluorine has a higher ionization energy. As you go down, it decreases. Sulfur should have a lower, fluorine a higher. So those trends reinforce. Fluorine should have the higher ionization energy. There will be a couple of questions like this on the test, guaranteed. Metallic character is another one. Metallic character includes the tendency to lose electrons. Metals lose electrons, nonmetals gain. We see that as we go across a period, the ionization energy increases, meaning it's much less likely that the ion is going to be a positive ion. Yes?
Does metallic character just the opposite of ionization energy?
Pardon me?
Is metallic character just like the opposite of ionization energy?
Yeah.
Okay.
So the metallic character decreases as you go across and increases as you go down. So it follows the same trend as atomic size. This one actually, I think, is the easiest one. So pick maybe row 4, period 4, and go across. These are metals. Then I'm getting into semi-metals and nonmetals. Well, the nonmetals must have less metallic character than the metals, right? I'm going from metals to nonmetals. Metallic character decreases as I go across. Let's pick maybe period 5A here, group 5A. Up here, I've got nonmetals, semi-metals, and a metal. As I go down, they're actually going from nonmetals to metals. Metallic character increases. That one should be the easiest. Choose the more metallic element. Well, tin or tellurium. There's tin or tellurium. Tin. That one really should be a no-brainer because tellurium is not a metal, it's a semi-metal. Tin actually is a metal. How about silicon or tin? Tin again. Tin for the win. So here's silicon, and there's tin. As we go down, metallic character increases. We've gone from a semi-metal to a metal. So tin, bromine or tellurium. Here's bromine and tellurium. So as we go across, metallic character decreases. As we go down, metallic character increases. So tellurium would be more metallic. And again, you can tell here, this is a nonmetal, that's a semi-metal. How about selenium or iodine? Yeah, that's one of those, the trends are bucking each other. They're both nonmetals. As we're going across, we predict that iodine would be less metallic, but as we're going down, we predict that iodine would be more metallic, so that's another one of those can't tell.